Okay, got like 1 minute till class. That's all right, we'll do a quick recap of last time in Applied Mechanics 2. And I'll get rid of the echo. So last time we left off, we were talking about pendulum that's not held with like a rigid kind of string or something, but a stretchable, maybe like a spring. And in reality, every pendulum has like some kind of stretching spring to it, because if you pull on a rope, the rope stretches and then it'll pull itself back. Everything's a spring. Like that's at least first estimate, you can say it's a linear spring. For the most part, everything's like non-linear. But if you apply a force to something, it will stretch, bend, compress something. And if you release the force, it'll have some restitution. It'll reform some way. So it's a spring. But anyway, we're thinking about the simple planar pendulum, but now thinking about with a spring attached to that simple pendulum. So we did a couple of things on Friday. Again, kind of recapping. We said, let's describe the position of where the pendulum is with its radius and its angle. Kind of makes, like, intuitively, it seems like something about that is going to make sense because the spring is always stretching along that radial direction. Like we can only, if we pull on the spring, we're always pulling it further away from where we call it the origin. And then angle will be our second degree of freedom, kind of like the two things that we need to describe where is this pendulum at any point. So the last thing we did was draw a free body diagram, kinetic diagram of our spring pendulum. I called it FS. You could have called it like tension or anything, but FS I used is like force of the spring and gravity. Were there other forces that I missed? This was what I had put on there. Nothing, at least nothing that like came up over the weekend. You didn't wake up at 1 a.m. like, my God, we forgot friction. But there shouldn't be friction, right? Like it's not dragging on anything. So we're good. Go back to sleep. Well, it's 1 a.m. on Saturday night or Sunday morning. I don't know. Depends. Then only new part here is this kinetic diagram. This is like our newest tool in dynamics. It's like, what is motion? Like, how does force relate to motion? And I drew it as radial acceleration. 90 degrees to that is some kind of like transverse or theta acceleration. So now we have 2 degrees of freedom. We want 2 equations of motion. How do we do that? What is the next step? So that was all recap. What do we do next? And I'll check in, see where people are at. If there are questions that you have, we can kind of field those, or I can come back up and answer. But I want to know, like, what do we do next? How do we get to an equation of motion? That's describing like our position. Radius is, RP is radius times RP argument vector. Coordinates would be, what is the exact wording? So at least the coordinates that we described would be like r and theta, some kind of radius, angle. So when we create equations of motion, they're somehow related like r and theta to force applied. Yeah. Cartesian, and then you would have to have like some relation of like what is theta in terms of x and y. Not sure. That's okay. So we're doing it together. Suffering. What is the next step? To be honest. Not sure. Okay.
I mean, I know we have to deal with like different forces like presented to you guys.
Okay.
I mean, I know it's what we consider. I think do we have to set these or no, because it's a motion.
Like you could say something forces minus mass times acceleration equals 0.
Yeah.
But it's the same as like that equals nothing.
Okay, I see. Yeah.
Okay. I only did a quick like survey of a few people, but it seems like general feeling is lost, not sure. There is a next step. What the heck is it? So let's back up a second, because we're talking about like a different version of a simple planar pendulum. What is the equation of motion for a pendulum, for like a simple pendulum? So if I have this one, if I have a pendulum swinging, mass m, length L, do you know what the equation of motion looks like for this? Or even what an equation of motion is? Like, we could start there, because this is not something that comes up in daily conversation. It's not like understanding how many calories are in a Pop-Tart or something, which I don't even know offhand. I would have to look it up. What is an equation of motion? Like, what is that even describing? Yeah. So it could be one way to think about it is like how it moves. Sometimes the actual motion is called like the solution of that equation of motion. So equation of motion should be a description of how it's moving, but it's a generalized of like for any initial condition and for any point in time, this equation is kind of holding true, something like that. So let's give the answer, because engineers, we love the final answer more so than like the derivation. Have you seen this equation before? Theta double dot equals negative g over L sine theta. Oh, you haven't seen this? What? Never? Physics 1, 2, 5? Never? There is no, I don't think there's a physics 5, I don't know. That one, it depends. If you take the class, it doesn't exist, but if you sign up for it, it's still there. It depends on what you observe or not. Physics 5. Not really, I made that up. Okay, so forget about this. We got tension acting up, we got gravity acting down. All this is equal to M-A-R, M-A theta. we do have acceleration in that radial direction. There's centripetal acceleration, but the radius is not changing. Kind of strange thing. So MAR is not 0, but it's not going to give us like an equation of motion. It's going to give us some equation that describes tension. But this is kind of general process, like same thing that we do in statics, where, okay, here's all my forces, let me just add them up. What they're equal to in statics, it's all equal to 0. Here in dynamics, they're all equal to the MA terms. So in my radial direction, I have a negative t, and then I have a positive mg cosine theta, and all that is MAR. In my theta direction, there is no t, like that tension from the pendulum is not there in the swinging direction. So it's a negative mg sine theta, and that's equal to ma theta. This is kind of the process that we use to get from, here are the forces, this is the motion that I'm trying to describe, get it into like an equation that I can actually solve. This part kind of bothers, especially like engineers, where we're used to like, give me a formula, plug in some numbers, get to the next step. But in this case, everything is a variable and everything's a function of time until we get to the final step where we actually say like, here's a differential equation, plug in some values. Sorry. A negative t? So radial, this is like my ER. This one is my E theta. I skipped over some of the steps. I was just like showing the quick and dirty. So if it's going away from origin, positive. If it's going towards origin, negative. So in this case, because I drew tension up and towards it, it's always a negative. If tension ends up being a positive number, then it's okay. Like it's just a constraint force to maintain the length is always fixed, but the way I drew it, it's got to be a negative. All right, so now I have AR and A theta. Those, once I chose my coordinate system is cylindrical, they have a fixed definition. It's a table lookup of like, if you're in cylindrical coordinates, acceleration is always these two terms. And they're in the textbook, but let's look it up. Polar coordinate and look at this. The very first image that we get is that acceleration is this thing, and I can copy it. And so I looked it up specifically because I just wanted you to know, like, it's never far away. Like, you can always find it or find someone who knows it. So that first term on the left is my like AR term. The one on the right is my A theta term. Oh, whoops. I meant to do this. And let's zoom in a little bit. All right, in this case, we have a 1 degree of freedom pendulum. If we know its angle, we know where it is. So what does that tell us about R? Do we know anything about that distance R from our origin? So what do we know about R? So in this case, the thing that I'm looking for is theta. Like theta here, theta there, but there's still an R. Like if I want to describe acceleration in a polar coordinate system, I need to know R, and I need to know how R is changing. So I need R dot, I need R double dot. What do I know about R because it's a pendulum of a fixed length? Yeah. R is constant, nice. What do we know about derivatives of constants? 0. So everywhere I see an R dot or an R double dot, it's all 0. Love it when stuff goes to 0. It's my favorite activity of just all this stuff. It don't matter. Just set it equal to 0, and now I have much easier equations to work with. The main one that I care about is the highest derivative. We can go through that in a second. Here I have a theta dot, here I have a theta double dot. So all I really care about is that theta double dot equation, because I'm looking for what is the equation of motion. It's got to be some second order differential equation. And then I'm going to replace R with L because we had a fixed radius of L. So what I was trying to get to here was like, how do I find that theta double dot? Because theta was all I was trying to figure out. If I know theta as a function of time, then I know its position, because I can always say like its x position is theta time, or like sine of theta times L, cosine theta times L, find like x and y positions. But theta was my main thing. If I know where that is, and I know where it is over time, so I'm trying to get to the point where I have a differential equation of theta in terms of either constants or varying things. So theta double dot is sine theta times that negative g over L. That's my equation of motion. That's the quick thing here. And this, you've never seen this one before? All right, welcome. Here we are to the world of pendulums. This is the simple pendulum equation of motion. This one's not, it's still simple because it's still describing just a point mass, like swinging on a rope. So it's not a compound pendulum, would be like distributed mass, or maybe like multiple masses or something. All right, bird's eye view, what we did. Draw a free body diagram. We did that for our spring pendulum. Find the forces acting in each of our coordinates. So here, radial and theta, so r and theta directions. Then sum up all those forces and the acceleration terms and set them equal to each other. And then the last step is like doing the math to figure out what is the equation of motion. Like you could divide through by m and try to find that theta double dot. Maybe it's a coupled term, maybe there's theta double dots and r double dots. But that's what we're trying to do. So let's rinse and repeat. Let's try it with a spring in there as well. What's our force of the spring? What would that one look like? KR? We could call it KR. So then 0 force is 0 radius. I'm fine with that. Yeah. We could say KR minus L if we want, but KR is fine. KR. Or we could say R minus L0 of like some unstretched length. But whatever you want to do. So give it a shot. What is, and let me copy, I'll copy up that. Do I still have it here? Yeah. There's our coordinates too, acceleration. So this is what we have so far. All right, so let me start with like the very first step of what we need to do. We're looking at vectors here. We're breaking down things into their components, and the fact that the components are at an angle is a little confusing, but it's not the end of the world. Like we've done it before, we can do it again. So ER is everything like along that tension or MAR direction. So I can say MAR is a negative K R minus L0 and then a positive mg cosine theta. And as far as like the first step, that's all I need. Like we'll do some algebra to figure out like what is the final kind of equation of motion. Then we can do even more like linearization if we want to solve it, but this is your very first step. What are the components along a given unit vector? What's along that MA theta direction? Is there any spring force? No spring force? Is there any gravity? There is some gravity. How much? Negative mg sine, so it's our sine theta component. We used up our cosine in one direction, now our sine is in the other direction. And at least this first step, it looks almost exactly the same as a simple pendulum, like there's, from what we had just kind of looked at. The only difference is now we have like a k times r term instead of that, like it's not tension's not constant, but a constraint force. So now it's tension with stretching. All right, so then I'm gonna get rid of this, make some room for myself, because the next step is plug in my definition of AR. And again, this is, you can derive, it's not magic, but for the most part, like if you're using polar coordinates, it's always the same definition for acceleration, so you can always look it up. You can always just say like, this is, everything's in a circle, and this is how I describe acceleration in that circle. And that's our main first step. From here, we can do as much algebra as we want to try to say like, this is the equation of motion, but we're just like getting to how do I describe those differential equations. So let's take a look at this ER to start. MR double dot minus MR theta dot squared, negative K what do we want to do? What do you think? M shows up a lot. We could try to get rid of the M's. Like a K over M kind of term. I could bring that R theta dot over to one side. So now I have like one of my equations of motion, but it depends on theta. So if I want to solve, if I want to solve it, I would need to know like what is theta as a function of time. So I also need that like theta equation of motion. Yeah. Can we integrate with respect to R? Not directly, because R is a function of time and theta is also some function of time. But yeah, so it's not, I'll show you like a way we can like separate them and turn them into two independent equations of motion rather than two coupled equations of motion. But at least for now, they're coupled. So we gotta go to couples counseling. So now we'll do the box and figure out the other person's, the other theta perspective on this. We have mr theta double dot plus m2r dot theta dot is negative mg sine of theta. Again, I'll get rid of those m's. R's come up here and there, so I'm going to get rid of it. So I have that g over r over here. M goes away. This one's like a 2 r dot theta dot over r, something like that. So in terms of like, you were told, show me what forces are acting on this thing, give me the equations of motion. This is it. I have r double dot is some function of r and theta, and theta double dot is also a function of r and theta. And then there's also a theta dot in there, right? So as long as you have the highest order derivative is a function of all these other lower order derivatives, it becomes a differential equation problem where now we can like move on to the next step of like solving the problem. But these are the equations of motion. Yeah, we still have a little bit of time left. I'm just pausing for a second. And I'm going to paste these again right here. Have you looked at like linearizing functions before? Have you heard of this? No? Squaring something? Usually you want to like unsquare stuff and like try to get everything, or 1 over something. Do Taylor series, does that sound familiar? Nightmares of Taylor series. Infinite series chasing you down an infinite hallway through an infinite hotel. My kids lately have had a lot of questions about infinity, like 7-year-old, 10-year-old. And they're like, well, how big is 2 times infinity? I'm like, it's still infinity. Like, that can't be right. I'm like, well, imagine you have a hotel with an infinite number of rooms. Have you heard this about the infinite hotel? Like an infinite number of rooms, and you get one, and every single room is filled, and one more person comes and says, can I have a room? And they're like, no, they're all full. I'm like, no, you can say, yes, he can have a room, he or she can have a room, because you could just have the person in room 1 to move to room 2, 2 to 3, 3 to 4, and just have everyone pick up their stuff and move to the next room down the hallway. And it's infinite. You can just keep going. Infinite squared. Yeah, then you get into like, because an infinite squared hotel is bigger than an infinite hotel, right? That one's... Sorry?
So, it's funny because you square it and it's bigger.
Yeah.
But you double it, but it's bigger.
Yeah, doubling does not make a difference, but squaring does. Because there's not a difference in like an infinite number of prime numbers versus an infinite number of even numbers. Or like odds and evens. There's an equal amount of infinity of both of them. Anyway, so linearization is like, yeah, these functions are infinite series, but as engineers, we don't need an infinite series to describe everything. So the idea of linearizing is like, can we get this to a simpler form just by making some substitutions? What's the, if I take sine of theta, what's the first order like linear term of sine of theta? If theta is small. Sorry? It could be 0. Yeah, so if theta is 0, sine of theta is 0. So one way, we could just say sine of theta is 0. What if it's like 0.01? That's pretty close to 0. What if it's like 0.1? Not 0? What could we call sine of theta? This is where infinity comes in, because sine of theta is an infinite series of polynomials. So I'll write out the whole thing. It's theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, theta 7 factorial, and then there's a whole bunch of like higher order terms. What's our linear? If I want to say I'm going to do an engineering approach, linearize it. Theta? It's theta, yeah, sine of theta. So if theta is small enough, sine of theta is theta. There is no difference for small angles. So it is theta. Plus higher order terms, but that's all right. What about cosine theta? 1? Yeah, should be around 1, right? Yeah, because this one is 1 minus theta squared over 2 factorial plus theta to the 4 over 4 factorial. So at least in terms of like linearizing sine theta, cosine theta, it's theta and 1. Those are nice. And again, all of this is like kind of extra work. This is very much an engineering exercise, because most of the time we're going to deal with like things that are changing just a little bit, and we want to learn how to control it. Like, how do I control it if I always want it to be around a given angle or near a given angle? So engineers, we linearize stuff all the time. Physicists, they leave it in open-ended, or they make like big sweeping generalizations about it. Okay, cool. So that gives us, paste it down here again. So this whole thing becomes negative g over r theta. This whole thing becomes a g. So now it's not quite decoupled, but it's getting closer, where we're like a little closer. In order to make the assumption that like sine theta is theta, we have to say that theta is much less than 1. What does that tell us about like theta dot? Yeah. It's also got to be real small, right? It doesn't have to be 0, but theta dot is also very small. What if I take a real small number and I square it? Tiny, tiny, tiny. So this whole thing, that's going to 0. So a theta dot squared, that centrifugal force, if theta is real small, centrifugal force is not going to be a big factor in this analysis. All right, again, I love crossing out things to 0. The last thing that we have to deal with is like, what do I do with this thing? R dot, theta dot, R. This one, so if R is not, so if we're not like bouncing way up and down, like it's not changing a lot, it's like maybe a spring just kind of moving up and down a little bit, I can say that like R is around L0, like L0 plus like a small delta R. Where delta R is really small, and if delta R is really small, then R dot is really small. And now I have another really small times a really small. And again, I love that because I can say that whole thing is equal to 0. And once I have all of those, now I've got this kind of, and I think some people were kind of looking for this answer when they were trying to look for like equations of motion. Like, is there a way that I can say R equals this and theta equals that? And there is, but you have to start off with like the general, here's all of the terms of A, here's all the terms of AR and A theta. Oh, we're over time. All right, sorry. Anyway, this is like to get to that final result. You can go through those next couple of like linearizing steps. Okay, see you on Wednesday. Yeah, we were teaching, but now we're leaving.